Okay, good afternoon, everybody. I'm Donnel Murray, and I'm from the SuperGrid Institute, in charge of the grid consulting services activity. We are very happy to be with you this afternoon to share the result of our study on a topic that is a real passion to us, multi-terminal HVDC grids. So those were seen for many years as we can say a futurist concept, but we will see during this presentation that they are today much more than a concept, and that the future is already starting. So I will present you briefly the agenda, and the different speakers will introduce themselves when they start their part. So in the first part, we will have Feasibility Crazy from Energinet introducing the topic and the North Sea Wind Power Hub program. In the second part, William Leon Garcia will present the main findings we had on this study that we performed together with the North Sea Wind Power Hub. And finally, Joris van Doorn from TenneT will share with us what are the next steps and the upcoming, let's say, the way forward towards those HVDC grids. And finally, we will end with the Q&A session. So for Q&A, we will have on two sides, so people in the room and also people that are attending online. For online participants, just a couple of words. So the microphones are muted and they will remain until the end. But you can write your question down using the GoToWebinar tool. You can even do that during the presentation. You don't have to wait until the end. And also when notification, this session will be recorded, and the recording will be available on the SuperGrid Institute YouTube channel. So I will now give the floor to Feasibility Crazy, who will introduce the topic to us right now.
Yes, as mentioned, my name is Feasibility Crazy. I'm a senior project manager from Energinet, and I have the honor of presenting the North Sea Wind Hub Consortium for you guys. If I can scroll. Yeah. The North Sea Wind Power Hub Consortium is a consortium which was established back in 2018 and consists of us from Energinet, TenneT Germany, TenneT Holland, and also Adequacy. We are a consortium who is co-founded by EU through the CEF fundings. And our main goal here is actually to see how we can deliver on the Paris Agreement. Unfortunately, we couldn't be there at Paris, but online would also work. So the Paris Agreement itself, as you may know, it tries to limit the global warming, trying to keep that under 2 degrees Celsius. From the Paris Agreement, we also can see that we need to have a massive change in the energy system, and so much more renewables are to be installed in order to deliver on that agreement. And where we see, depending on which reports you read, it will be anything from 280 to 350 gigawatt of offshore wind, with a substantial amount of gigawatt of interconnectors. We could also see that if something needed to be done differently in order to be able to deliver on this, the current rollout is just simply too slow in order to be able to meet these requirements. And this is where we slowly come in as a consortium. We believe that there is actually 3 main needs here. The first one is the need of sector coupling, enabling transportation of the demands to the transportation of energy to the center demands, seeing how the sector coupling itself, electricity with molecules could work like, but also the integral system development, see how we together on an international level can coordinate the planning of the the wind production in the North Sea. As shown in the figure here in the middle, there will be multiple thousands of lines going crossing each other, and then that is also was something that could and will bring some challenges to it. So there is where we try to see how can we utilize these energy sources in more better way. And here comes our model, which is called the model of hub and spoke concept. For those who lives in Denmark and has, or also for the people who lives in the world, has played with the Lego. Our approach is to try to build something that is a more or less Lego blocks, which can be step by step, scalable and expandable in the future. If we look into these energy islands, it will be a hub and spoke, meaning that they will be interlinked to each other, but also sending electricity to shore or sending the power to the mainland as mule cools, not only as electricity. What we have done in the North Sea Wind Power Consortium is we have tried to develop this philosophy, and we believe the key is international coordination. That is also why we are here together with multiple TSOs trying to solve this. We believe that it requires international coordination in terms of seeing how the power to gas, for instance, can be matured onshore, offshore, and so on, but also in the hub themselves to see how they can be optimized. So the foundation type, we've been looking into multiple different types of it, everything from sand island to Kasong Island, then to platforms. North Sea Wind Power Hub is not only a technical consortium, which could sound like when we look into this technical, webinar. The North Sea Wind Power Hub consortium consists of other work streams as well, where some of them are very much into the energy market to see how we can provide the access to market, make the market open, provide the incentives for the stakeholders in order to be able to be part of that enormous market that will be there. Then also the other one, which is trying to see how can we start to plan something which is beyond 2030s. That is also another work stream on this. This is mainly to see how we can minimize the footprint of the impact that we will have out there. And then the last work stream we have in the North Sea Wind Power is that we have this regulation frameworks and planning procedures that we try to see how we can plan things for the next decades to come. You can always build a island as cheap as possible, but that could easily make life much more difficult to the ones that comes after it. So we're trying to see how we can plan us out of it and try to somehow minimize the cost for the future islands that are to be installed. And then a few words about what we can deliver on. Someone may say that those things are delivered on, but what we are trying as a consortium is we will call the policymakers to consider much more long-term renewable energy targets, also including offshore wind. Call the policymakers to consider long-term international coordination on marine special planning. As you saw, there will be thousands of cables going in and out of the North Sea, and it just requires a lot of planning there in order to reduce the footprint, environmental footprint of it. And then also we would like to invite the Dutch, German, and Danish governments, and of course also the European Commission, to consider to set up the cross-governmental consultation and to support development and hub and spoke projects. And also, as we have done, invite the industry to continue the discussion and dialogue with us to see how we can facilitate this rollout. Yes, these were the KPIs or the goals of the North Sea Wind Power when we started back in 2018. And someone may say they're all checked out. Not only because of us, but a lot of people has put a heart into it to make this delivered. We saw back in June at the SBR declaration where most of these bullets here were achieved. We know that the neighboring countries, Denmark, Belgium, Netherlands, Germany, has already agreed to plan for 65 gigawatt of offshore wind by 2050. So things are moving forward, and we're really glad to be part of something that is so enormous and such a great paradigm shift in the way that we have been thinking about the energy systems. So now I will leave the floor to William Leo Garcia, who will talk more technical aspect of it.
Thank you, Fitim. So here, William Leon Garcia. I'm a technical business developer at the SuperGrid Institute, where we're an R&D and innovation center in Lyon, in France. And so we recently, last year actually, we did feasibility studies for the NSWPH consortium. So I'm going to present 3 parts, and the first one is the adequacy design. So for the next 20 minutes, I'm going to talk more technical in this part. So keep awake, please. And for this first part, I'm going to divide it into 3. So adequacy studies first, protection studies, and a comparison between different kinds of internal interconnectors. So NSWPH study case is a really complex case. It is a huge MTDC network connecting up to 6 different countries. So I'm not getting into detail on this architecture, but in order to optimize this system, consortium came up with the idea of breaking down the system into smallest pieces, so giving birth to what we call block type concept. And the block type, it's consisting of a small part of the system, usually around the DC bus, where you can find some components like the MNC converter, the transformers connecting to the AC side. And in this example, we can see 3 departures that are named internal interconnectors, which typically transmission cables in the offshore wind case, since it is a subsea cable, and they connect to other block types. In another block type, you can also find a spoke, which is a term used to the part that is connected to an AC network onshore, or also through a transmission line. And so these interconnectors can be either DC or AC, depending on the case. And this has to be compared from economical and technical aspects. And we're going to do this during this adequacy study. The advantage of these block types is that it enables a modular development of future MTDC networks. So this is one of the first, let's say, modular approaches, the NSWPH case. And for the expansion of multi-terminal grids, you can interconnect these block types in different ways to create the meshed MTDC network. And you need to ensure to find the best interconnection among the different, let's say, wind farms and the onshore AC networks as well. So, of course, there is always a base case. You know which countries you want to interconnect, which wind farms, but the way it is meshed inside can be more or less configured. So, how to ensure that this system is cost-effective while it meets the adequacy and the AC system constraints. And that's why we wanted to answer in this project, proposing a step-by-step heuristic approach. So to avoid using really powerful or let's say time-consuming optimization program, we analyze it small step-by-step, and we also use a tool, an in-house tool that we use to compute performance indicators that I will come back later. So in the first step, you need to take all the data you need. So costs of the components, reliability, and the first, let's say, define topologies of block types. So you can come out with a first comparison among them and compute what's the transmission capacity of a given block type, what's the break-even distance to choose between an AC or DC interconnector, and so on. And the second step, you need to do perform a load flow analysis that will give you what you need for the adequacy study, and you can estimate an amount of energy curtailment that at the end will impact the cost benefit on the benefit of your solution. And then you focus on the internal interconnector itself to determine if you, let's say, there you will use more data about the reliability of the components you need in case of using an AC or a DC interconnector. And according to the capacity of each interconnector, you determine also an optimal length for which you can decide if to use either AC or DC. So at the end, you configure the different block types. You have your first feasible architecture, not only one, but several solutions. So we up to tens of solutions that then you can compare using key performance indicators among them. So the key performance indicators that we need to use for comparing these architectures are mainly effectiveness indicators, which are the total loss of the overall system, the transmission capacity of each one of the interconnector, the reliability indicators that are the expected energy not transmitted, so it's related to the curtailment of your installation, so what energy you lose because of the reliability of every component in the system. And finally, economic indicators, so the investment cost, the capex, and the operating costs that are taken into account by at the end by the total expenditures, which depends also on the cost of the energy at a given time, and the previous indicators as well. So just to be more concrete about this, there is an example here. So you can see a table where we compare the three different interconnection types. And so whenever the case is red, it shows that the cost of transmission capacity is less for the pure AC internal interconnector topology of a given block type. The yellow one means that hybrid solution is less costly in terms of cost of transmission capacity, and the green one for the complete DC solution. So you can see that for different amounts of power here, which are in PU, there is a distance at which pure AC solutions is more interesting than DC solutions. So DC is usually for longer distances, and hybrid solution that also has some interest in some cases. And so this is a pure, let's say, economical comparison. But in the second part, in the third part, we will see that there is more things to see whenever comparing this AC and DC. That more, say, related to the dynamic behavior of the system, formulations and so on. You wanted to ask something, but maybe. Huh?
CAPEX-based or levelized cost? Not levelized cost.
No, this is CAPEX-based by the transmission capacity of the line. Thanks for the question. And so when comparing this kind of architectures, so we use at the end we compute what is the total expenditure, what you were saying, the total life cycle cost of the system. So you can see that in an example where you need to put a redundancy on an internal interconnector, so you need to, when you put two DC lines, for example, with respect to the original case scenario, which is 100%, you need to spend a little bit more. Let's say no. First, you have a little bit more losses here, so 1% more, and you need to spend 4.5% more. So you have a capex increase as well. But when you look at the expected energy not transmitted due to this redundancy, which means due to the load flow analysis that we perform, we can say that you reduce by 35% the amount of energy not transmitted. So at the end, this reflects in a TOTEX reduction of 2.8%. So this is one of the comparisons that we did in the study. If you want to check the complete study with the complete comparison and solutions, it's available on the NSWPH website already. So some takeaways of this first part to conclude is that so we propose a generic methodology to perform this adequacy study, and you have 3 degrees of freedom there. So whether AC or DC interconnection, you can choose. The capacity redundancy, so how many cables you put in there, and how you can interconnect among the block types. Okay. The data also, you need the data from the TSOs and from the people that's in the field that knows about the reliability of the different technology that exists today. So the breakers, the lines, the cables, the converters, and also the market, maybe some market profiles about the consumption during the year, so you can deduce the power flow in the system during the full year. And that's first part is say about the adequacy itself. We are just comparing economic indicators. But once you have decided what is the best economically feasible architecture for the system, then you need to study how do you protect the system against any disturbance. And that will also impact a little bit this first adequacy, because we will add some more components, which are the protection components, DCCBs and switches, for example. So the protection of an MTDC network will take part since the occurrence of a fault. So let's say a short circuit on a line. So this will cause the system to lose voltage and power for some time. And we need to be fast to detect where the fault is. So in the first part, the fault current strategy will locate the fault and interrupt the fault current. And the protection also will take some role the instance after the fault interruption to recover fastly the voltage and then put back the power through the DC network. So it goes until this post-fault power restoring step. And so this protection strategy will be a series of algorithms and well sequenced in time that will depend on how the architecture of the system is done, how the grounding is done. So all this are input parameters to select this strategy and calibrate the strategy, and then it will impact what technology is compatible to be as performant as you need to protect the system as you need to. But since here we're talking about design of the protection system, you have to take into account the surrounding transmission system, which is the AC system. And so you need to define a framework based on the active power interruption and the impact on the frequency reserves, because you need at the end power to compensate the interruption of this active power, which is taken from the restoration reserves, FRR, and the containment reserve, FCR. So here you need to match high probability fault scenarios to low AC system threshold. For example, like if the stop is temporary and lower than 150 milliseconds, so you have a high probability fault, you can use up to 1 gigawatt of the restoration reserve. But if it is a permanent stop, you need to use the containment reserve up to 1 gigawatt. And so the lower the probability, the less severe the threshold will be, and but also the impact will be larger. So you will not only impact a country, but 2-3 countries, or even the European area, depending on the city. It's a very different. And these probabilities are used to classify, let's say, some events and give some linings to the protection design. So as a matter of example here, where there is a line fault in the HVDC grid, so the one here in red, so you cannot allow to any of the converter to block. You need to be selective and isolate this line. So in this case, it is not allowed to disconnect a wind farm, a wind farm converter or a onshore converter that is connected to the spoke, or any of the adjacent converters. But for a lower severity, or let's say lower probable fault, we can admit to disconnect the wind farm MMC that is just next to the bus bar that is in fault, or the spoke one, but you cannot allow to disconnect any other ones that are farther in the system connected through other block types. So this will give a framework to design the protection, and I will show an example later to illustrate better. But first, you need to know also that in the MTDC system, the DC buses can be configured in different ways and will have different impacts on the security of the system. So there is one bus bar topology that is called single bus bar, single breaker. So the breakers that you need there are only 3, and with 4 switches, you can perform. Let's say if there is a fault, you will lose power for a longer time. Let's say, to simplify. If you use a double bus bar single breaker here, so you have the same amount of breakers, but you use more switches, so you can reconfigure the bus bar to be faster at the recovery or maybe seamless in case of faults. There is a one breaker and a half. They have more breakers, so to double the breakers, and you have still more switches. And in the double bus bar double breaker, you have up to 8 breakers and 17 switches. So this just to say there are different possibilities of bus bar topologies. And to study the impact on this, so we use the same KPIs, so taking into account the system data. And so for a block type, so this small block type analysis, if you consider the block type has a maximum power of 2 gigawatts, these 3 topologies here are all compliant with AC stability constraints, so you can compare them. And depending on the topology, you will have more or less expected energy not transmitted. You will see that the yellow one and the green ones are similar, but since you allow less energy curtailment in the double bus bar single breaker here, this one will represent a TOTEX. This is the TOTEX actually of a reduction of 8% with respect to this reference value. But then if the block type is of 3 gigawatts, sorry, I forgot the title here. This is for a 3 gigawatt block type. So since if there is a fault on this bus bar, you will lose 3 gigawatts. So if you remember the adequacy, the AC system criteria, you cannot afford to lose this amount of power. So this will not even be considered. It's not feasible to use this configuration: single breaker, double breaker, single breaker. So you need to compare only between the last 2, which are the most expensive one, but the one that it's 1 breaker and a half ensures less cost of the co-protection system. I will come back to this later. This is the cost of the DCCP and the DC reactor in yellow. So with this, all this set, you chose the bus bar topology, you chose the protection components, not still. You need to choose what the protection components you need at each departure. So here, just not to get into detail, but for fault 1, for example, this fault 1 is inside the grid, and it's on a line. It's a line fault. So we said it is high probability, and so it's the most constraint one. So we need to be selective and open both breakers at the adjacent, at the ends of the line. For case, so that's why it's F1, and for case F3, it's a busbar fault. It's less probable. So you can afford not afford to disconnect the adjacent system, which goes through this breaker. So you need to put a breaker there to be selected. But this single MMC, whenever it's a fault in the busbar, you can afford to lose it, so since you're not losing more than 2 gigawatts, and it's connecting a wind farm. So you don't need a breaker there. You don't need a fast opening. You can open an AC breaker on the other side 100 milliseconds after, and then you can use a switch here. So that kind of reasoning we use, taking into account all these constraints to choose what technology is feasible and more economical for a given let's say, situation in the network, to optimize the network at the end. So I don't have time to go through the simulation, so just to say there are some breaker limits to respect, some converter limits to respect. So we also performed during the study an EMT to be sure that the choices we made are enough in terms of transient behavior and dynamic behavior of the system. So all these limits are checked during this kind of studies. So to conclude, of course, we can affirm that the full selective fault clearing strategy is feasible for this kind of networks. A busbar topology assessment allows you to choose cost-effective topologies. So let's say what you need for the specific protection need of the grid. So you don't oversize all the time and you put breakers everywhere. And so if you can allow to, this is this is technical perspective for future work. So if you can be more precise on what are the AC constraints, because here we use the grid codes and what people already are used to due to the normativity in AC. But if you can study better and be more precise on what are the AC constraints, maybe you can also be even more cost effective and reduce some of the AC constraints to allow like non-selective fault clearing strategies to be considered at some points of the system. And also the DCCB costs, which I will talk again later, will be something that has to be assessed, since now we know that there are different options of DCCB technology out there in the market that are almost ready for DCCB, and if not very mature, industrially mature already. So this final section is the technical presentation. It's the part for the comparison between AC and DC interconnectors. So on the one side you have the DC internal interconnector option, in which you have a DC line connecting two MMC converters that are at the same time connecting to a wind farm collector grid. In this case, both AC collector networks are non-synchronous, so they are not connected in the AC, so they have their own. They are not synchronized together. But in this case, you need to install what you need for protection for this DC line, that are the DC breaker and the DC reactor. So this now has to be included into the analysis, because as you may think, this is an offshore platform here. So if you put a breaker there, so you're gonna need in space in the offshore platform, and this will be very costly. So this has to be assessed. In the case of the AC interconnector, so it has less transmission capacity, so you need two lines there. The network is the AC collector network. It's a single synchronous AC grid. You need an additional transformer to suppress the offset, DC offset that will appear between both MMCs. And so this is to take into account into the economical study. I forgot in the last slide, but in here as well, the MMCs on this part are controlled in grid forming control, so they support the voltage and frequency of this grid. So in this one, both independently, but in this one they coordinate to control voltage and frequency. So both solutions are compared in terms of capex first. So in blue, the AC solution, and in red, the DC one. So one of the main conclusions here is that the cable costs are negligible, actually, in comparison with the cost of the rest of the components in the DC bus. So this difference here is mainly because you need a DCCB and a DC reactor in an offshore environment. So that's why DC is, in terms of capex, you need more investment to implement the solution. It started becoming more interesting at the break-even distance of 20 kilometers. So I don't get into details for which scenario was this comparison, but once you compare, you include the OPEX on that. So all the losses and the converter and cable losses, you can see that the AC solution has more losses, up to 3.5% more. And it has even less transmission capacity than DC solution. So at the end, when you compute your TOTEX, you will see that actually DC solution is more interesting. So for this specific case, I'm telling it's more than 1000%, but it's not always the case. But in this case, for the load flow that was in that point at that block type, this was the answer there. So, and generally, DC is more interesting than AC. Really fast at some few kilometers. So we also did the MT simulation studies. I don't want to get into detail. I just say we did some fault scenarios. So in the lines, what we call an internal fault and an external fault, that is an MMC blocking, is to see that when you perform a dynamic studies, you can see here in red that for the case of an MMC blocking, since I said both MMCs were connected to an independent AC network, when you lose one MMC, you lose the whole wind farm there in the DC interconnector solution. So you lose the power. So for AC case, it is seamless because it is a asynchronous, it is connected to AC, so you can still pass from one wind farm to the other because there is a redundancy of AC cables. For the fault at the interconnector, in the DC case, it is seamless because you have a fault at the line and it is selectively and rapidly isolated by the DC breaker. So you can still operate. But on the AC case, the AC breaker is lower, so you have a loss of power during 100 milliseconds, and you have some transients after. So it's seamless for a DC. So to conclude here, we saw that there are even here that even if capex and the breakdown distances were in favor of the AC solution, the TOTEX, which includes OPEX and PE and T, showed once more that the life cycle cost is much more interesting. The dynamic performance observed with EMT simulations show the interest in both solutions. So you need to integrate what you think you can lose additionally in dynamic study to the initial static study that you performed for the curtailment and the first economic indicators that we compare. It's just you take into account the load flow, but when you do simulations, there are even additional more curtailment from the dynamic behavior of the system. So you need to see that as well. The simulation will be very important up to feasibility study in a project like that. So EMT studies are very important, and maybe a hybrid solution when you put both AC and DC, it will require more investment, but maybe in terms of curtailment and the dynamic behavior, you will at the end reduce even the topic. So we don't know, but this is for further studies of this kind of projects. So this is the end of my part. Thank you very much. There is a small question. I don't know if we can do it at the end, yeah, if it's okay. Just okay. 2 minutes. So give the floor to Joris Van Doorn, who's from TenneT online.
Yeah. Good afternoon. Thank you very much. I'm Joris Van Doorn, indeed from TenneT. I work here as an HVDC technologist, and yeah, thanks for listening in. I have the honor to present the next steps we foresee.
Sorry, Joris. Can you hear from there? Can you speak louder, please, Joris?
Yeah.
Perfect.
Is this better at your end?
Yes, good.
Yes.
Okay, then I repeat myself shortly. I'm Joris Van Doorn from TenneT, work here as an HVDC technologist, and I will present you the next steps. Yeah, there we are. Yeah, we think the next step is standardization is really important. We should focus to make DC as simple as AC, where standardization is key to fulfill this rapid rollout of renewables across Europe. And yeah, Donuel already started with it, like it's not anymore talking only about concepts. Now, multi-terminal DC is seen as a possible solution to have a faster rollout of renewable energies. And also here, the Esberg Declaration, which Team recalls, signed in May 2022, writes about this. It writes about 65 gigawatts offshore 2030 and 150 gigawatts in 2050. That's a very rapid increase. And it also contains this declaration, this collaboration between the Danish energy island and Belgium to have there the first energy hub interconnected, and also writes about a plan to establishment of more DC hubs, more energy hubs on the North Sea. So then about standardization, what do I mean with this? It is to create here together a common technical language for high voltage multi-terminal DC. And then I talk about all the components in the system indeed need to be happy as a single family. Cables, converters, fault separation devices like breakers in there all should work in harmony. But also think about a master controller which should be there to provide set points across the whole network. Is very important to make such a next step. And for this we need to set clear direction in developments where block types and directions for internal interconnector and protection strategies are then highly important. Where we of course not should forget usage is key. We use this onshore AC grid already for decades, and this multi-terminal DC grid should fit in as much as possible as we can. And one example I would like to give here is the maximum loss of load or maximum loss of generation, which is allowed by countries. For example, Denmark currently 700 megawatts, the Netherlands about 1,000 megawatts. And those bipolar converters of a bipole of 700 megawatts and a bipole of 1,000 megawatts should all work together in a single multi-terminal DC grid. And how should we do this? And here we should make innovative steps to bring such a system to practice. And the next step is really, I think, to prepare. And here, North Sea Power Up, together with SuperGrid, has taken this next step in the development of functional requirements for multi-terminal DC grids. And to explain what we mean with this and on which level this requirements is, I have this picture on the bottom left, and I started at the bottom. There we start with the idea, 2018, an energy hub at the North Sea, where we went to a pre-feasibility phase, doing conceptual design, describing purposes and needs of such a system. And then last year we did the feasibility phase. William just showed you the results of this, more the architectural level of such a system, where the focus is on the main topology, bipole with DMR, and the various topologies of bus bars and so on. And we're now entering the pre-feed state. We are currently working on these functional requirements, where we take in the point of common coupling of AC. We should bring such a multi-terminal DC system within the current AC system. And this study then focus on the point of common coupling of DC. And they're also again looking in towards modular HVDC building blocks, such that we could standardize and make a rapid rollout. So we do this study all underpinned by EMT, and we're really looking forward maybe presenting you next year around this time the results. Yeah, with this I want to finish, and I would like to give the floor back to Daniel.
Thank you very much, Joyce, and thank you to all our speakers for this sharing this amazing vision about HVDC networks. So we have some time left for questions. I think we have some questions already in the room. So maybe you can ask your question. Yes, please.
Yeah. Two quick questions. The first one is around the problem study. And did you look at the bus bar and DC circuit breaker failure mechanisms in your case list? And if so, why were they not a high priority issue for power loss in the study you saw? That's the first question.
You want to go back to the which slide you said? You wanted to.
We were talking through the scenarios. You mentioned your maximum loss cases, and you mentioned cases of line faults and line faults, including a DC circuit breaker failure. So there would be an additional zone of failure as well. I was wondering why busbar failure and DC circuit breaker failure was not included in that list.
Ah, okay. Busbar plus DC breaker failure. Okay. It's a good question. Actually, since I was not in the studies myself, I'm not sure why they did not choose this option. It's true that it's not here. Like busbar plus DCCB failure. It's on slide 21.
I think it was evaluated, but the probability is extremely low.
Yeah. It must be that.
Then
yes.
it was not conclusive in terms of loss.
Because in the table you see it's already in green, the line fault plus DCCB, but it's busbar was already less than the line, so it's very, very less probable.
And the second question is,
yes,
comment is really about the EMT studies analysing long AC spokes. I totally understand that you've got to consider the power division, and that's included. But I guess the issue that I couldn't see covered is the small signal instability you get from that long AC line connection, and that can preserve up to a third of the rate of the converter. So there are other cost impacts that come from a detailed examination of these options. I guess it's just raised. You'll have to robust calculator. Probably extra things to look at.
Yeah, I think that's.
You're right.
I don't know if that's part of the transmission capacity. When we say transmission capacity,
it was not considered. But it's a good point. Yes. Yes, please. You have a question also?
Yeah, my first question is about backup protection, but I guess it's kind of covered the real question. The second one was regarding the AC interlink. I'm not sure anymore which slide that was, but that interlink becomes longer than a certain length. In addition to having additional transformer, you may also need reactors, which will take up additional space. And if the AC link is normally closed with all switches, which you immediately want to exchange, have the interconnection function between different companies. Yeah. You may also need a chopper offshore and all the extra energy that is there in case of failure. Is that something that you guys also include in the cost estimates?
Actually, we went into these details, but the chopper was not required to what we evaluated. So it was we were able to run down with the wind turbines, and there was no the chopper needed. Any other question in the room? Yes, please.
Maybe a follow-up question. Do you know what type of background speed you need for turbines?
I cannot give you the value by heart, but you can find it probably in the paper.
Another one, on the DC side, you know, these blocks. So every time you connect a block, you're changing the DC side. Will you then, or you then go back and reconfigure the converter every time you connect a block? Also, let's say part one, then you start configuring, you connect part two, but change the TJPs. So probably part one needs to be adjusted. So will that be done every time like new part?
Yes, this is something that should be evaluated in further studies, right? As much as possible, as it would be only, let's say, configuration on the converter. This would not be a big issue, but what we are trying to achieve in this standardization, of course, is not change the hardware, but to have the equipment that can be extendable, scalable as much as possible. But of course, there might be some issues if the overall grid is not planned from the beginning. We might have power flow issues, different issues. Yes, please.
Sorry, just another quick point about that diagram we put on the board. It's just to say, it's showing a monopole arrangement, but if you happen to have 5 HVDC solution, and then you're cross-coupling on your AC side, so rather than having one bus bar, you have 2, you end up with quite a lot of resilience shared between the HVDC network and the AC network. So there's games you can play around how you do connectivity, to give you more capacity, and avoid using DC circuit breakers straight away, and avoid them on all but circuits to take out.
Which case you would have to do the monopole thing.
Where's the detail?
Yes, please.
May I ask, the detailed analysis of this contribution, is it published somewhere in a paper or?
Yes, the results are published in 3 different papers that were presented at ICREST conference.
Right, would you be able to share the title of the papers of the whole paper?
We
Oh yes,
have a flyer.
we have a flyer introducing the paper, so you have it at the end.
Thank you.
Donald,
Even the full report is in the NSWPH website.
And it's also available on the NSWPH website. That was your point, Fitim. Yes, please.
Regarding the operation time of the DC breaker, another very large impact on how long I think for the main study, you assume a certain type of breaker with 2 millisecond operation time. Then you use 5 milliseconds. Could you comment on that margin?
Yeah, I saw that I know 5 minutes.
5 milliseconds, it was. Yeah, 5 milliseconds. Oh, sorry.
Normally it's below 3 milliseconds, right?
It can be. It depends on the technology.
I've seen some.
So we wanted to be conservative in this study, and also to be as much as possible technology agnostic. So we took a value that would enable most of the technologies, and this was the feasibility was then yes.
Continuing on this, if you consider also the case that a breaker would be significantly, let's say, smaller footprint and faster operation time, then in some cases would you choose DC over AC in these cases? Is there some, I think there was a slide that showed that the DC breaker and the reactor have large impact on the cost, comparing some cases. How sensitive is this proportion to the cost of the DC?
It's a big impact, especially for offshore, because any footprint impact is multiplied by the cost of the platform. So that for sure there is a big lever.
So if the reactor could be half the size and footprint half the size, then how big would be the change in the selection for AC versus DC? Things that you would flow.
It would be even lower for sure, but it's mainly the breaker. So reactor is not that impacting in terms of footprint, but the breaker today it's a huge impact for sure.
I think the message at the end was not only this investment cost, but also the total you have to do for it.
We have this sensibility analysis. You can find it in the
Okay, yes.
on the report. So maybe we switch to online questions.
Yeah, there are 4 online questions. So the first one, do you also consider in your study the fact that for radial mesh grid, there is a requirement for new grid code, especially because of the large renewable power generation?
This is one of the keys. So maybe, Joris, you can take the question, as it is more a TSO question, I would say.
Could you please repeat the question, because I cannot hear all the audio from the from over there.
So do you also consider in the study the fact that radial mesh grid, for radial mesh grid, there is a need for new grid code, so the DC grid code?
Yeah. Okay. Yeah. This for a total mesh grid, indeed, a DC grid code is needed. But you could also think of it to have, I would say, intermediate steps in here. That maybe this first international connected HVDC hub could be by a bilateral code between the TSOs or countries involved here. And of course, such an operational framework, maybe then to put it like that, should be, I would say, compliant with the AC grid codes over there. And it could be in the end the front runner of such an DC grid code. Yeah.
So maybe another question.
Yes.
So the rest.
So which type of AC fault, line to ground, line to line, or 3 line to ground for 150 milliseconds and FRT?
Ooh, this is accurate.
No, I can say that 3 line to ground is a more severe one.
Yes.
We need to take into account the more severe case.
Yes, that's true.
So I don't know which slide it's relating to. I only know it was used.
I was to the slide with the table of FRT on it.
Okay, so then there's another question. Here the example are with MMC half bridge VSC.
Yes, it's MMC half bridge.
Okay. Another question. It seems that the figures for double bus bar, double breaker, and breaker and have been switched in the presentation of protection.
It's true. I just noticed that. Sorry for this. It's just the representation that are switched with double breaker and one breaker.
And
that's it on that. Okay.
Thank you. Thank you very much.
Sorry.
You can address directly to us after.
You said you use half bridge. If you have used full bridge and got out the DC breaker, would that change a lot the outcome? Like taking another protection strategy?
With a full bridge? Yeah. Actually, we not really fully investigated the option, but with full bridge, the amount of losses is highly increased. And yes, it's not, you still need a braking device, so maybe you just reduce the size. But and the losses are too much high actually to be competitive for what we studied so far, but it was out of the study, so it was just an investigation we have done.
If I can just mention the fact that this presentation was recorded and will be available on our YouTube channel, and through our website. So you can always review, reconnect, and contact us for any questions for the discussion.